Mhm.
Okay, let's get started. So you guys are awfully quiet. You should definitely give me feedback so I know if I'm going too fast or too slow. Shoot. Uh-oh. Okay, there we go. Okay, so let's start with a little bit of a recap. So we're trying to understand networks of spiking neurons, and our starting point is an equation for a coupled set of neurons, tau dvi dt equals minus vi minus e leak. And we looked at a current-based model in which we divided neurons into excitatory and inhibitory, sum on J of W, I, J, E, G, J of T, minus the sum on J minus the sum on J of W, I, J, I, G, J. So this is excitatory neurons. See. So these are excitatory neurons. And these are inhibitory. Neurons come in two flavors. They either excite their postsynaptic neurons or inhibit them. Okay. And sort of tau is around 10 milliseconds. That's going to become important. And in this sum, there are about, in both of these sums, there are approximately 1,000 non-zero terms. And what that means is each neuron cortex each neuron in cortex connects to about 1,000 others. One thousand other neurons, which is kind of a small number. So you have 100 billion neurons in your brain, and each one connects to a very small fraction of the other neurons. Okay, so we started off making some really, really severe approximations. First of all, so approximation one, oops. So the approximations we made. So approximation 1. So we're, by the way, going to drop all these approximations eventually. So 1, so Wij goes to We. So all neurons have the same connection strength. Have the same connection strength. So same connection strength. But we need to be clear if they're connected. Okay. So the true story is Wij equals We if neuron J is connected to neuron I. Neuron I. And 0 otherwise. Because remember, each neuron connects to a massive subset of the other neurons. So we don't want to set all neurons, make for all neurons to something non-zero. And the other approximation we're going to make for now, again, this is temporary. And that is, we're going to replace Gj E. Of course, this goes for E and I of T. Goes to the time average, GJE of T. And that is just the firing rate of neuron J. Excitatory firing rate. But because we've made this a approximation that all neurons have the same connection strength, because we made that approximation, now all the neurons have the same firing rates. Okay, neurons are indistinguishable, and so that made things massively simpler. I'm just going to draw it here, and then I'm going to redraw it on the next page. So these assumptions, these approximations, tell us that the sum on J of Wij E Gj of T goes to just K, number of connections per neuron, times the strength of the connections, times the excitatory firing rates. And the sum on J of Wij Gji of T goes to K Wi. Okay, and K is number of connections per neuron, which I'll assume is the same for every neuron. And again, that assumption I will drop as well. Okay, so that's a recap of what we did last time. And what we're going to do now is in some sense, given these extreme approximations, we're going to solve for the average firing rates. We really only have two numbers now. The two numbers are the average excitatory firing rate the average inhibitory firing rate. But even those are going to turn out to be, in the simple model, the same. Okay, so that's what we want to find. And that turns out to be, even with these extreme approximations, harder than it looks. Okay, so our equation now is tau dvi dt. I'll keep the subscript I. Some sense makes things easier. We'll think of this as some test neuron sitting somewhere in their network equals minus vi minus e leak plus, things are much simpler now. It's k we nu e minus wi nu. And we'll assume now that the net firing rates are fixed, so this is just constant. Okay. So the picture we have, so this is a rate of change of voltage. The picture we have looks something like this. So this is E leak, which remember is around minus 65 millivolts. And up here is threshold. This is threshold, call it theta. And this is about minus 50 millivolts. And then basically we have this quantity here. Let's say that the K we nu e was up there. So what happens is we start at leak, the membrane potential is pulled up, do this differential equation up to here, it gets to this point, it emits a spike and gets reset. And the same thing happens, it gets pulled up, emits a spike, and is reset. Okay? And this time here is T spike, and that's what we want to compute. Okay? Now, for the neuron to spike, we need to have this quantity here above the threshold. Okay, if, for instance, it was down here instead of up there, what would happen? In that case, the neuron would never spike. It would just go to there and not spike, which makes sense. The synaptic drive has to be large enough for the neuron to actually spike. Okay, so we're going to solve this differential equation. I did it last time. And if I remember correctly, I just wrote down the solution, which you should verify. And that is that VI of t equals, actually, let's write down VI of t minus E leak. So this is a solution when the neuron doesn't spike, equals K. So equilibrium, it's going to equal K WE nu E minus WI nu I times 1 minus e to the minus t over tau. That's assuming at t equals 0. Okay, so this guarantees when t equals 0, so VI at t equals 0 minus E leak equals 0. because e minus t minus 0 is 1. And vi at t equals infinity minus e leak is equal to k w e nu e minus w I nu I. Okay, and that's what would happen if the neuron doesn't spike. Okay. So if there's no spike, this is a no spike case. Okay, but in fact, once a neuron reaches threshold, so vi, so theta minus e leak, which we'll call delta v, equals k w e nu e minus w I nu I times 1 minus e to the minus the time of a spike divided by tau. Okay, which is what we did last time. And now if you solve for t spike, you get so t spike over tau is equal to log minus log of one minus delta v divided by k w e nu e minus w I nu. Okay, is that right? Yes. Which means the firing rate nu equals 1 over time to spike. This is number of spikes per second, equals 1 over tau divided by minus log 1 minus delta v divided by k w e nu e minus w I nu. Okay. So we actually don't yet know how big w e and w and wi are. We're going to find that out in a second. But we should plot this. So first of all, as we saw earlier, so this distance here, this distance here is delta v. The distance between threshold and resting membrane potential, and we need KVE to be larger than delta v. Okay, and we see this in our equation. If this quantity here, so if this quantity here is less than delta v, this log is negative and it's undefined. It's basically infinity. What that means is the neuron never spikes. So we have to have k w nu e minus w I nu I greater than delta v. And when that happens, so this number 1 over t, so tau is 10 milliseconds. So this quantity here is 100 hertz. 100 hertz, 100 spikes per second. Okay. So if we were to plot this, nu versus, so nu versus basically k w e nu e minus w I nu I. Okay. So below, if that's below delta V, it doesn't fire. So this point here is delta V. And it goes up very steep, very quickly, depending on what W is. So it's not long before it gets to about 100 hertz. And it just keeps going up and up. Okay. Now, one thing to keep in mind is that, let's go back to this picture. So in this picture, there are no fluctuations. Okay, we made the approximation, if you remember that, so we made this approximation here. This approximation here, these terms which are actually fluctuating in time, replace them by constants. Okay, that doesn't really happen. The true story is that, getting a little ahead of ourselves, but the true story is that instead of going straight up, this actually fluctuates. So even when neurons are fluctuating, even when this quantity here is less than delta V, which means in a no fluctuation case, there'd be no spike, there can actually be a spike. So the true story is this curve actually goes like this. So the green is no fluctuations. And this term is the true with fluctuations. And neurons, so these are fluctuations due to spikes. So spikes come in okay. So the picture we have is the black curve is our current modifying rate, and the green curve is what we actually have once we put fluctuations back in. Okay, so we're just going to write this as so the first observation, of course, is that nu E and nu I have the same firing rate. So because of our very simplifying assumptions, so basically nu E equals nu I, call that nu. And so our equation is, we have a single equation of firing rate in terms of firing rate. So nu equals, I'm going to call this nu zero times some function of k WE minus WI nu. Okay, because and psi, it's called psi of x equals 1 over minus log 1 minus delta V over x. And nu zero equals 1 over tau. 100. Okay. And psi here, this black curve, is nu zero psi k WE mu E. Okay, so that's our so-called firing rate. It's output firing rate is function of input firing. And so we're going to solve this graphically. So in this axis, we put k WE minus WI nu. So we know it looks like this. N versus nu. And there's equilibrium. So this is a line, the 45-degree line. 45-degree line. And this here is in equilibrium. Okay? This is a point where nu, at this point, nu equals nu 0 psi k WE minus WI. Okay? So the value of that equilibrium depends, of course, greatly on the weights. Okay? If the weights are really small, in fact, if the weights are really small, they go to 0, for instance, then this is the case where the weights are really small. This goes like this. So these are really small weights. There's actually no equilibrium at all, right? The neurons, the network can't sustain itself. So the weights have to be above some threshold for the network to work. So we kind of need to know how big the weights are. And that's where we left off last time. And last time, remember, there's an experimental fact that if you take two neurons, you record spikes from one of them, so you stick an electrode in that neuron, and you record the voltage versus time, and these neurons are connected. So you make this neuron spike, you actually do experiments where you stick another electrode in here and cause this neuron to spike. And you plot the voltage, of course, it sits at rest, and this is the time of the spike. Pre-submagnetic excitatory, it goes like this. And this is an E neuron, EXE. If it's inhibitory, it keeps doing this. If it's inhibitory, it goes like this. This is excitatory. EXE. But in either case, the amplitude here is about 1 millivolt. 1 millivolt, maybe half a millivolt. So when a presynaptic neuron spikes, it produces a PSP of about a half a millivolt. And we can solve for that, which we did last time, by writing down the equation for the voltage when a neuron spikes only once. So daddy feet, when single neuron spikes, equals minus VI minus E leak, plus we have one neuron, and these things are all the same. We'll do excitatory neuron, GJ of T, and we'll set this quantity equal to E to the minus T over tau S, synaptic time constant divided by tau S, and again theta of T. This just tells us that the T is less than 0 at 0, And tau s is for excited turn neurons is typically 1 to 5 milliseconds. So it's much shorter than tau s. So you want to solve this differential equation, and the solution, which we had last time, is vi minus e leak is equal to a e to the minus t over tau plus b e to the minus t over tau s, which you can easily verify is the only solution. We plug that into our differential equation, and we get minus ddv ddt either brings out a minus 1 over tau or minus 1 over tau s. So we get minus a e to the minus t over tau. I'll do these in different colors. Minus b e to the minus, minus b tau over tau s e to the minus t over tau s equals, now we're looking at this term here. So there's a minus sign, we get minus, we get minus a e to the minus t over tau minus b e to the minus t over tau s plus we e to the minus t over tau s divided by tau s. Okay, shoots. This was supposed to be in green. Okay, think of these as green. And so what we have is, first of all, this term cancels. Those terms are the same. And when we solve for b, back to green, we get b is equal to we e to the minus t over tau s divided by tau s times 1 minus tau s, which we'll write we, should use a subscript e, e to the minus t over tau s divided by, it's actually a minus sign, tau minus tau s. Okay. So our solution, remember, was b plus a. So why do we have the a? We have the a because at t equals 0, let's go back to this plot. So at the arrival time of a spike, this time right here, v is actually equal to e leak. So we enforce that, we get v, we get vi minus e leak is equal to we e to the minus t, w divided by tau minus tau s times e to the minus t over tau minus e to the minus t over tau s. Okay, we're going to write this as we over tau e to the minus t over tau s. Sorry. minus T over tau minus E to the minus T over tau S divided by 1 minus tau. Okay. So basically, it's WE over tau times this quantity here. And what we want to find is the maximum. So this curve here is basically it's double exponential at T. So this term here, figure out its properties, red. So this quantity here, so this is equal to 0 when T equals 0. The whole quantity inside these brackets. 0 as T goes to infinity. And somewhere in between it has a maximum. So we plotted it, it looks like this. It goes up and comes down, okay? So this quantity here, it comes up, it comes down. We want its maximum. And the maximum occurs, it's not hard to show that the maximum, this has a maximum as E to the tau S over tau log tau S over tau divided by tau S over tau minus 1. That's the EXP. Okay. You should verify that. It's not so hard. A couple lines of algebra. Doesn't really matter. So this quantity, this maximum occurs if tau S equals 0, the maximum is 1. Tau S equals maybe 1 or 2 milliseconds. So we're just going to call this number, we're just going to give this a name. We're going to call it, we just call it Cmax. Cmax. Okay, it's just some number. It's around 1, maybe a half, maybe a third, depending on the value of tau S. So this quantity here is our PSP size, V called ePSP. Okay. So what this means is WE, which I've also called WE, I think, is equal to tau V ePSP over Cmax. I'm gonna call it give it a name E. And similarly, WI, which I've also called WI, is equal to tau V iPSP. The inhibitory side of it, inhibitory synaptic potential, it can be positive or CI minus. Okay. And so now the quantity of interest, if you remember, is K times WE minus WI. So K WE minus WI is equal to K. I'm going to put a tau here. So we have V ePSP over CE max minus V iPSP over CI max. Okay, and I'm just going to give these a name. I'm going to give this quantity here. Let's call it delta V0. I call it delta V PSP. And I call this quantity here, so this has got this name. This name I'm going to call it G, delta V PSP. Okay, this quantity here is now equal to K tau delta V PSP 1 minus G. Okay, so if we go back to our firing rate equation, which was this here, we have, oops. So we have nu equals nu 0, which is, remember, it's 1 over tau, divided by minus log 1 minus delta V, distance from threshold, divided by K, number of connections per neuron, tau, the time constant, delta V PSP 1 minus G times nu. Okay, and this whole quantity here sort of sets a scale for the firing rate. So delta V, remember, is about 50 millivolts. That's the top. K is about 1,000. Tau is 10 milliseconds, which is 0.01. 1/100th of a second. So this is K. This is tau. And delta V PSP, CE max is less than 1, so we'll call this, just to make it easy, approximately, let's say, 1.5 millivolts. Just to make things really easy. So this is about 1 in units of actually hertz. Okay. So what we get is, so when we do that, we get nu equals nu 0 over minus log 1 minus, I'll give it a name so that we don't call it, let's call it, because we've got units of hertz, call it nu let's call it nu, we're using too many symbols, nu W, because it depends on the weights, divided by 1 minus G nu. Okay. So this is nu, and this is nu, this is approximately equal to 1. Okay. So now assuming G is less than 1, let's say, what this means is that the firing rate, first of all, it goes up very rapidly. So nu 0 is 100 hertz. So now we can actually put scale bars on this. So this is new. On this axis, we're going to plot this quantity. So right here is nu W over 1 minus G. That's where it starts going up. And once it goes up very rapidly. So we'll say 1 minus, let's say G is a half. In a little while, we'll see that gets regulated. So this is around 2 hertz. Okay. Once the firing rate goes over 2 hertz, it goes up very rapidly. By the time we get to, let's call this 4 hertz, 4 spikes per second, we're up somewhere around 100 hertz. Okay. So this is the scale. This isn't really to scale, right? This goes up very, very rapidly. And if you draw the 45-degree line, it actually looks like this. This is a line, nu equals nu. We have an equilibrium here, right here, at low firing rate. Okay, around a couple hertz. Okay, so this is a picture, right? So basically, we've used we've used so we haven't, in some sense. I mean, the analysis was kind of complicated, but in some sense, we didn't do that much, right? We started with this equation. We started with this equation here. Okay. We made some approximations that look pretty severe, but we'll be able to drop those. And then we did some math, and we basically used the fact that when people do experiments, a PSP or memory change will change when there's a single spike is about 1 millivolt. And what we got is that, firing rate is a function of firing rate. The equilibrium is at very low rate. Okay. And this curve here goes up very steeply. Okay. In some sense, neurons in the brain, because they make 1,000 connections too. Each neuron makes 1,000 connections, and PSP is at 1 millivolt. Neurons are very strongly coupled. Okay. So let's take a quick 5-minute break. And when I come back, I'm going to introduce something new, which is going to be stability. Okay. So this is an equilibrium. If all the neurons are firing exactly this value, they'll stay firing exactly this value. But what if there are small fluctuations? What happens? And once we do that, the story gets slightly much more interesting and slightly more complicated. Okay, let's take a 5-minute break. Again, it would be nice to have feedback. Am I going too fast or too slow? You can put it in the chats or email me. Either one is fine. I haven't seen any chats. Let me see. Okay. Oh, shoots. Is there an echo? Yeah, there's an echo. I'll turn this off. Okay, that should fix it. Okay, so let's now. So we have this equation here. This is sort of an algebraic equation for firing rate in terms of firing rate. Let's now actually, but this doesn't. Things don't happen instantaneously. All right. So if the firing rate at the neuron at some as if you have fix a firing rate of the network of the neurons in the network at some time, there's going to be a lag. So what we're gonna do is write new. Oops. So new t plus some short time later. We don't really know what that is. Equals new of t plus. So new 0 psi of our firing rate, which we write as new w 1 minus g new to be consistent with what we were doing earlier minus. So this is actually, we're introducing in some sense a new concept of sort of dynamics and with some kind of delay. So this is in some, we can think of this term here as sort of our drive to the neuron. So drive to the firing rate, right? If at time t, this is at time t. If at time t that, the neurons are firing, with some delay, the neurons are going to, if this is positive, so this is positive, then nu goes up. If it's negative, nu goes down, okay? So basically this is, remember, it's nu equals, the current time, and then plus that quantity, okay? And we're going to approximate this every now and then my pen stops. We're going to approximate this quantity, which is very common, as a Taylor expansion. This is nu of t plus delta t d nu dt. Okay. That equals nu of t plus the term in brackets. These things cancel. And we get an equation, delta t d nu dt equals nu 0 psi of w 1 minus g nu minus. Okay. So this is a differential equation. It's nonlinear, which makes it hard to solve in general. So it's nonlinear. But although we can't solve it in all generality, we can do stability analysis. So let's assume that nu 0 is an equilibrium. So we're going to now do stability analysis. Okay. And what we're going to do is assume that nu 0 is an equilibrium and ask about the dynamics nearby. This is a classic technique that you guys should know about. Hopefully you've seen it at some point in your life, because it's not exactly straightforward. So we'll assume that Oops. So assume that, so we've already used new zero, okay? So new star equals equilibrium. And what that means is that new zero, our flying rate function of new W, 1 minus G new star equals new star. So this is the thing we wrote down earlier. So that's the equilibrium. That's basically, it's this point right here, right? Where it's an equilibrium. And what we want to do now is ask, is that equilibrium stable? Okay, and the way we're going to do that is we're going to we can't solve this differential equation in detail, but we can solve it if we let nu equals new star plus delta nu, call it d nu, call it delta nu, and write down an equation for delta. Okay, so d dt of delta nu is equal to psi 0, psi nu 0, psi of nu w 1 minus g times nu star plus delta nu minus nu star plus delta nu. Okay, so that's exact. What we're going to do now is Taylor expand this and write this as approximately equal to nu 0 psi of w 1 minus g nu star, and then plus delta nu d nu star of nu 0 psi 1 minus g nu star, then minus nu star minus delta nu. And these last two terms come from that term. Okay. Okay, so now we have cancellation. Oops. What happened? So this term here, because it's in equilibrium, cancels with the new star. And this thing is equal to, say, ddt, delta nu dt is equal to delta nu times dd nu star of nu 0 psi of, sorry, this is nu w, nu w, nu w 1 minus g nu star minus 1. Okay, so the sign of this matters. So if this is positive, implies equilibrium is unstable. Is unstable. Okay, because if that's positive, delta nu grows exponentially. Right, it's d delta nu dt equals a delta nu, then delta nu equals delta nu 0 e to the at. So if a is positive, it grows exponentially. If it's negative, implies stability. Okay? And whether or not it's positive depends on whether or not this quantity here is larger or smaller than 1. Okay? And that quantity here is a nice interpretation. It's how rapidly our gain function changes as we change nu star. And we only have to go and look back here to see that the slope is greater than 1. So the slope here, so the slope is greater than 1. Greater than 1. So that implies that this fine weight equilibrium, which we found, is, according to this very simple analysis, not stable. Okay? So we've done kind of some it's not too hard, but it wasn't too easy analysis. We made some approximations, and what we found is, according to this very, very, very simple theory, that there is no low fine rate equilibrium. Neurons can't, networks of spiking neurons, because they're strongly coupled, can't sit and fire at low fine rates. So that's clearly inconsistent with experiments. And so we've made a mistake somewhere. And the mistake we made was way back here. Well, basically, we said everything was sort of the same, and we basically said the excitatory inhibitory neurons have the same fine rates. That's fine at equilibrium, but away from equilibrium, it's not true. Okay. So what we want to do is analyze excitatory inhibitory firing rates separately. And so we're going to do that. We're going to actually change things a little bit. If you remember, so back when we made our approximations, we said all neurons have the same strength, right? And that's what's true for WE and WI. So we somewhere in here we made the approximation. Must have written it down somewhere. Oh, it was here. Basically, we said Wij. So this neuron here was sort of your typical neuron. We didn't bother to distinguish between excitatory and inhibitory neurons. So all neurons got the same coupling. So all neurons have the same function. So we're going to change that a little bit. We don't really have to, but it's much more realistic. It's going to make things, in some sense, conceptually simpler later on. We're going to write tau d VI E dt equals minus VIE minus E leak plus sum on J of W H E E. This is going to be our equation, G J E of T minus the sum on J of W I DJ I T. There's going to be another equation for tau dV I dt. And the difference is that we're going to have, instead of E here, we're going to have IE and I. Okay. Then we're going to average. We're going to do the same thing as before. So Gj of t goes to nu. I'm going to write tau dBi. I'm going to use Q here. Dt. So Q is going to equal E or I. This allows me to write the same equations sort of more succinctly. Minus BIQ minus E leak plus. So we're going to do two things. We're going to and the other thing we're going to do is we're looking at Wij QE go to WQE if there's a connection. If there's a connection. Okay. So those are the two approximations we're going to make, which was the same as the ones we made before. So this becomes K, number of connections per neuron, WEE, mu E, minus K, WEI, mu I. Sorry. This is WQE and WQI. Okay. And now we can, the other thing we can do is we can actually, so all neurons have the same firing rate. So we can just drop the subscript I. So this really just becomes the firing rate of the whole population, all the excitatory, all the inhibitory cells. Okay. So this is two equations, two unknowns. Remember, this quantity here is approximately equal to 15 or so. Somewhere around that range. These numbers are pretty big. Okay. So what that means is that we sort of have two equations. We have nu E, these are equilibrium equations. So the equilibrium equations look like nu E equals nu zero, or 100 hertz, psi of K WEE nu E minus K WEI nu I. And nu I equals nu zero psi KWIE nu E minus KW. Okay, so those are the equilibrium equations, and that tells us the value of the equilibria, which we're going to find in a second. It doesn't tell us their stability. First, we'll find the equilibrium and then their stability. And let's write down the equations we're going to use for dynamics. As before, we're going to write slides have gotten out of order. Let's kill that. Uh-oh. Sorry. Slides seem to have disappeared. This slides got moved out of order. I'll put them back in order. So this is our equation. We're going to now look at stability analysis. So we're going to write nu E of t plus delta t. I'm going to put an E here because there may be a difference. Equals nu E at time t plus this is nu E at time t plus, remember as before, nu 0 psi of k w e nu E minus k w e I minus d. And as before, we're going to write this as nu E of t plus delta te d nu E dt equals nu E plus this. And we're going to cancel and we're going to cancel these terms as before. We're going to give this a new name. We're going to call it tau E, the excitatory time constant. And our equations become then tau E d nu E dt equals nu 0 psi of k w e nu E minus k w e I nu I minus nu E and tau I d nu I dt equals nu I psi of k w I e nu E minus k w I nu I. Okay. So these are the equations that we want to solve. Okay, it's a little harder. Before we had a single equation, a single unknown, now we have two equations, two unknowns. And that adds a fair amount of difficulty, but it also makes things much more interesting and much more realistic. Okay. So what do we want? So how are we going to solve these? We're going to solve them in 2 steps. So in step 1, find equilibria. So that's new east. The equilibria are the solutions to these equations. So the equilibria basically are the solutions to this equation. So that's a 0 and that's a 0. Okay. So those are the equilibria. And step 2 is step 2. What is going on? Okay, step 2 is determine stability. So just like we did before, we first find the equilibria, and then we ask, is it stable? Okay. So this is kind of, so finding equilibria, and it's kind of complicated. So what we're going to do is we're going to do something called null Klein analysis. So if you look at the equilibria, which I'll write down, actually I'll just copy these over. So I'll copy these over. So the equilibria let's erase this. And erase this. So our equilibrium equations are that. Actually, I'm going to write it on the other side. Equilibrium equations are nu E equals that, and nu I equals this. Okay. So those are equilibria. They're also called null Kleins. So each of these curves, both of these things represent a curve in a 2-dimensional space. So if you basically said, I'm just going to solve this thing, this is a curve. This is a curve in nu E, nu I space. Okay. And what we're going to do is find both curves. We're going to find curve for the excitatory term and the curve for the inhibitory term, and where they cross is an actual equilibrium. Okay, so that's the plan. And we're going to probably get through one of these curves. Maybe we'll get through both. Okay, so we want to find this curve, and it's a pretty nonlinear equation, so finding a curve isn't that easy. So what we're going to do, though, is we're going to do it graphically. And the advantage of doing it graphically is it gives you a lot of intuition of what's going on. So what we're going to do is plot So down here, we're going to plot, this is going to be nu E. This is where, on this curve, on this axis, we're going to actually put the curve. So what we're going to plot on this axis is our firing rate curve. So this quantity here is nu zero psi of k w e nu e minus k w u. Okay? And we're going to plot this curve for different values of nu I. So this curve here is the curve when nu I equals 0. Okay? And we're going to also plot on the same plot, we're going to plot the 45-degree line. So this is going to be, in some sense, this axis is also nu E. And this is where curves intersect. Okay? And again, we're going to have an equilibrium. Okay? We're going to find the equilibrium. And so when nu I equals 0, there are two equilibria. One here, this is a classical view. So this point here, it sort of doesn't really on the curve, says, you know, if no neurons in the network are firing, then no other neurons can fire, right? No other neurons. None of the neurons are getting input. The classical view is that if no neuron gets input, the network's not going to fire. So that point is clearly equilibrium. So when nu I equals 0, there's an equilibrium here and an equilibrium here. Okay? So those are 2 points on this curve here. This is our null line. So it's 1 point is if nu E equals 0 and nu I equals 0 on the right-hand side, the nu equals 0 on the left-hand side, or if nu E is 0, but nu I is 0, but nu E is some positive value, you got the point there. Okay, that's the point we saw earlier. So that's nu I equals 0. We're now going to actually now increase nu I a little bit and draw a new curve. You draw a new curve that's going to look like this. So this is nu I greater than 0. Okay? We still have the same equilibrium here, so this is maybe nu I is a little bit bigger. So this equilibrium is shifted over. Okay? Looks something like that. As we make nu I even bigger, this curve here just keeps going up, right? So this whole point is an equilibrium of the network. Adding an inhibitory firing rate is not going to make the neurons stop firing rate, and this keeps this kind of going up. Okay? Eventually, if nu I gets high enough, it's going to look like this. Okay? It's going to look like this. So, and in between, it's going to look something like this. So it's actually, these neurons, these curves here saturate for real neurons. Maybe not our gain function. Oops. So if we kept following this red line up, there's actually equilibrium out here as well. That's getting a bit messy. So there's a point also on the graph out here. Okay, and these points also and these points here, unlike the other ones, move in a little. So if you look at this intersection here, it's going to be it's in a little bit. So what happens is curves come to here, and at this point here is where these curves peak. Okay, you get some kind of curve that looks like that. It's an upside down parabola, more or less. It's got a quadratic maximum. And so this is called the excitatory null line. Okay. So this was probably kind of fast. And it looks more confusing than it is. Okay. Basically what we're doing is so 2D curves are hard. So we fix the value of inhibitory neurons and plot a 1D curve. These are these black lines. They're just our firing rate versus firing rate curves. And we look for these intersections with a 45-degree line where nu E equals this, right? We're just looking at the intersections tell us, we're just looking right here. Okay, the thing I circled, where nu E equals this complicated nonlinear function. Okay, and in some sense, this should be kind of intuitive. If I fix all the firing rates, all the excited of inhibitory neurons, the network can sort of have 3 firing rate states. The network can be just shut off, no neurons fire. That's this point here. Or it can fire at a really high rate, right? The recurrent connections are strong. If the excitatory neurons start firing really rapidly, it's going to basically push all the neurons to high firing rate, and it's more or less the maximum. Okay, so this is a maximum around 100 hertz. Neurons can't really fire that, although with our fire. Good. And in between, think of this as a threshold. Oops. So right here, this is a threshold. Okay. If the neurons fire, if the excitatory firing rate starts above the threshold, they'll go to the maximum. They start below the threshold, they'll go to the minimum. Okay. So that's the excitatory null line. We're pretty much out of time, so I'll stop here. And next time we'll make the inhibitory null line and the intersection. The inhibitory null line is actually a lot easier. And to make the inhibitory null line, we'll look at the intersections and then we'll look at stability. Okay. And so we'll do that next time. And as usual, I'll put all this on the website with the graphs, hopefully in the right order. Okay. So I'll see all of you on Monday. And as usual, feedback is much appreciated. Okay. See you next week.